Good evening, everybody. Um, First thing I'm going to do is go over some of the stuff that we've started discussing already, particularly types of variables and some of the graphic display of some information about descriptive about statistics in general. Um, it may seem like we're like beating a dead horse here. Why is this like type of variable stuff? Why is that so important? Well, as we go on in the semester, you're going to realize that the type of variable that we're dealing with, whether it's categorical variable, an ordinal variable, a numerical variable, that's going to have a lot to do with the way that we analyze it, the type of statistics that we use. So understanding and recognizing the types of variables is going to be eventually very important to us. In case you're wondering, instead of blowing this up and running it like an ordinary PowerPoint presentation, I'm going to step through it uh, through the side window here because if I blow it up, it'll cover my whole screen. I won't be able to see the chat window and respond to questions and stuff like that. So I'm stepping through it this way on purpose. Okay, now data types. We've discussed data types. Now I want to just break that down for us for a second. Okay, basically we're dealing with two kinds of data types. First of all, we're dealing with nominal data, right? The base there is name, right? And we're dealing with numerical data. Okay, those are two main categories of data types. Within nominal, we're going to be working with just plain names, right, or categories, as they're called sometimes. And we're going to be dealing with ordinal data. So what do we mean by that? Well, when we're dealing with names, we're dealing with, say, car makes, like Honda, Chevy, Ford, or it could be gender, male versus female, or it could be whether a person has a disease or not, diabetes, yes or no, right? The yes or the no being the two categories that you might have within a nominal variable, which represents whether a person has diabetes or not. Now, ordinal is also typically based on a word or a name, except in this case, we're dealing with something that has some relative information about the value of of each category. For instance, if we're talking about grades, right? You might talk about poor, fair, good, and excellent, right? Well, those are all names, but poor is worse than fair, and fair is worse than good, and excellent is better than all the rest of them. So this order, even though it's a nominal variable, a name, the order, they actually do have some order. Another typical version of an ordinal variable is the pain scale from 1 to 10, right? How much pain are you experiencing right now? You guys are in public health. You probably have asked somebody that question, right? And typically, you ask them, well, from a range of 1 to 10, how much pain are you in? Well, you know, if they answer 7, that they're saying that they have more pain than if they had said 5, and less pain than if they had said 9. Right now, what is that? That 5 and that 9 and that 7, they don't represent absolute values, actual numbers, because one person's 7, maybe another person's 5, and so on and so forth. All you know is that relative for that individual, relative to 5, if they 7, it's greater. If they say 5, it's less. If they say 3, it's less. And the other thing that we don't know is the distance between the two of them. Is the amount of pain different? Is the amount of pain you experience the same difference between 3 and 5 as it is between 7 and 9? Right? There's no way to really define that. So that's a special kind of variable. We call that ordinal. It's a form of nominal variable, but since it has some sense of order, we give it a special category. Now, numerical is a whole nother class of variables that we deal with. They're numbers, obviously, right? So now we usually split that up into two groups. One is discrete, and by discrete, we usually mean just something that's generally an integer, right? For instance, the number of siblings that you have. Well, I have 3 siblings, or you have 2 siblings, and so on and so forth. It's always going to be a whole number, okay? And the other one would be something that would be, say, something like scalar, or you might call it scalar or numerical, and so on and so forth. There's a number of different names for numerical that you might come across. I think SPSS happens to call that scalar data. Okay, and that can be a number that's on a continuous scale. like blood pressure. Blood pressure is on a continuous scale from 0 to actually no limit, whatever would be the highest number, right? You can have decimal places in between each number and so on and so forth. So if I were to ask you how many cups of coffee that you had today, how many whole cups of coffee that you had today, anyone, and I told you I had 6. Anybody want to hazard a guess as what kind of variable that is? I know there's 20 of you out there, one of you. It's a discrete numerical variable. Thank you very much, Katie. I didn't even have to pull, God, another answer. I didn't even have to I didn't have to pull teeth with this group. This is terrific. On the other hand, if I asked you, what's the average number of cups of coffee you drink per week? Well, that might be 6. In other words, if we had 6 today and 4 tomorrow and 3 the next day and 5 the next day, that might be 6.5 cups of coffee. In that case, we're talking about it's not necessarily a discrete numerical variable. It's a scalar variable. Okay, so they can disguise themselves both ways. Okay, so now this open to a little bit of interpretation, but really the real reason we're interested in this is because down the road somewhere, it's going to affect how we're going to handle this data. So let me go back to what we were talking about before. Okay, get that out of the way. Nominal, ordinal, scalar. It's that numerical. A lot of times you see that referred to as scalar also. Numerical, discrete, basically integers. Nominal could be categorical. Nominal, sometimes you'll also see it called categorical. And ordinal is just another form of nominal as well. Okay, so there's a few examples of it that you can go over for yourself later on. Okay, the other distinction we'd like to make is that very frequently when we refer to certain kinds of numbers, those numbers may be associated with the entire population, or those numbers may be associated with a sample from that population. Okay, so if I were to, for instance, let me pull this back up again. You guys are going to come across these symbols quickly enough, but just for argument's sake, I'm just going to pull up we all know what the idea of a mean is, or an average. Okay, a little bit of what I'm talking about that'll come up later on, but we know that a mean or an average is just the numbers that get divided by the number of the frequency, or the number of numbers. Okay, so if I'm looking at the mean of a population, right, that would be designated by a Greek letter mu. If I'm looking at the mean of a sample from that population, I would instead use the symbol X bar. Okay, sometimes you'll actually see me write it as X bar because I don't. It's easier for me to do it with a computer than put that bar on top. Right? That's a statistic. So we have population as mu. We also call that a parameter, and we take a sample's mean. We call that a statistic. So when we're working with statistics, we're working with sample information. Okay, population, we call that a parameter. Okay, so that'll come up later on again, and we'll go over that in more detail. Okay, so let's go back here. So that's the difference between a parameter and a statistic. Parameter, you're dealing with population. A statistic, you have something that, describing a sample from that population. Yeah, scalar and continuous is the same thing. Okay, another way of saying the same thing. Prevalence of the disease in a population, parameter. Median age of 32 randomly selected subjects. That's a statistic, right? Because it deals with a sample from a population. Mean number of children per household from the U.S. Census. Anybody want to hazard a guess? The mean number of children per household from the U.S. Census. Is that a statistic or parameter? Are we dealing with a population there? It's a parameter, right? Because interestingly enough, we very rarely have information about an entire population. One of the main reasons we're learning statistics is because we want to be able to infer information about an entire population by taking a reasonable size sample from that population. Right? Very frequently, it's impossible to get all the information from an entire population. The one exception to that, what we see commonly, is a census. Okay, we run the census every 10 years. Is the census ever corrected statistically? In other words, for instance, I know in New York City that there probably are a large number of undocumented people that are living in New York City. Do we correct the census? We know that we actually could sample and get a rough idea what percentage of people that it is. Is that corrected in any way? Anybody know if that's corrected when we do the U.S. population survey? When we do the census every 10 years? It isn't corrected. Anybody want to know? Anybody know why it's not corrected? Okay, well, it's part of the Constitution. It's actually the census. The census of people in the United States is part of the United States Constitution, and it requires an actual physical count. You can't correct it statistically unless somebody passes an amendment to allow a statistical correction to the census in situations where it might be undercounting or overcounting people. So that's a little bit of trivia about the census. Okay, so descriptive statistics. Well, normally when we're dealing with nominal variables or categorical variables, the thing that we're interested in is frequency. How many of each are there? So, for instance, here we have nine. We have nine subjects in this case. You can count them. First person's male, second person male, female. So when we separate these out into two variables, the two variables we have, the variable that we have with single variable, excuse me, is gender. Okay, and what is gender? Gender is either male or it's female. And in this case, the frequency of males is 4 and the frequency of females is 5. Okay, we might actually throw up a bar chart which indicates the relative number of males and females, so we could look at it graphically. But with where nominal variables are concerned, our main interest is in the frequency. That's the first thing that we look at when we evaluate it. Now, unlike that, with numerical variables, we have a lot of other measurements that we can use. Okay, so for instance, with numerical variables, if I have a list of many numbers, let's say I have a list, this is a list of 5 numbers. One of the ways I'm interested in analyzing that data, say that these numbers are samples from a population. We picked out 5 people randomly from a population. We picked out 6 people randomly from a population, and these are the numbers that we got. Okay, one of the things that we're interested in is where's the middle of this distribution of numbers? Where's the middle value for this? Where is the average or middle value for the blood pressure in this population? Where's the average or middle value for blood sugar levels in this population? Okay, so one of those measures of central tendency, one of those middles is called a median. Okay, and the way we analyze median is basically it's just the middle value. You know, have an odd number of values, the median is just the middle value. So if you have 2 below, 2 above, if you have an even number of values, it gets a little bit hairier because you don't really have a middle value, so you just take the 2 middle values and you average those. Okay, so physically that's the way you would do that. We're going to be using statistical tools. It's going to be making it a little bit easier for us eventually, but it will eventually make some sense for us. The other kind of central tendency we're interested in is the mode. The mode is which values come up the most frequently. Okay, so let's see what the mode would be here. Let's see, we got 20s, we got 330s. So the mode here, the value that comes up most frequently is 30. Okay, so let's see if we have that there. Okay, the most important of these statistics that we deal with is the mean. Well, you've seen this in a lecture. You've seen this representation of the mean, and the Greek symbol sigma represents the sum of or summation. And we're going to take all the values, all the x's, all the individual values from 1 to the highest value, from the first value to, if we have 100 subject, first value to 100 subject. In other words, we're going to add up all of the values for every subject from the first one to the last one, and we're going to divide by the number of subjects, by n. That's going to be our mean. Okay, so for instance, our mean for this particular value, sum is 550, sample size is 10, so the mean is going to be equal to 55. We're going to do this exercise. This is so far we're doing stuff that's pretty simple. Now that we've gotten beyond just where the center of a sample or population is, now we want to examine something else, and that's called, and that is basically a measure of the variability. Okay, and they're called variance and standard deviation. They become a little bit trickier, and I'm going to break away from this for now, so that we'll come back and look at these formulas in a second. We're going to perform an exercise that actually does what's in these formulas. Okay, and I'm going to open up, if you want to go along with me, there is on Blackboard, there is a file called One Descriptive Statistics Exercise 1. Okay, and I'll open that up. There we go. Okay, and I'll give you guys a second if you want to open it up in the background also, so you can work along with me. Okay, you guys can still hear and see me, right? Okay, good. All right, just had to check that for a second. Okay, so I'm going to give you a chance to open up this file. And in this file, we see that there is a variable x, whatever that happens to stand for. It could be anything. These numbers, maybe it's diastolic blood pressure, for instance. That seems a little high, right? Whatever. Let's call it blood pressure, just in general, for argument's sake. But the numbers could represent anything. Okay, so we have 18 subjects. This person's a subject, this person's a subject, and so on and so forth. Goes from here to 19, 2 to 19. That's 18 different numbers that we have. And first thing we want to know is, where is the middle of this distribution in numbers? So just looking at it, it's kind of hard to interpret how these numbers are distributed. So one of the things that I'm interested in is, where's the middle of this? Okay, and that would be the mean. Okay, so the mean is going to be equal to, well, first thing I'm going to do is I'm going to count how many subjects there are. There is actually, now remember in SPSS when we first started working with Excel, when we first started working with Excel, if we wanted to create a formula inside of a cell, we would start with an equal sign. Okay, there are a number of different functions in Excel that you can use to do various arithmetic, statistical, so on and so forth operations. We can actually, if we go up here to the bar at the top here, where there's a little f of x, fx up here, and also you'll see that in the PC version as well. If I click on that, it'll bring up a window where it'll give me a chance to examine all of the different kinds of functions that are available in SPSS. Okay, I'm going to use one right this second that's called count. If I type in count, right, it actually describes that function for me. And it actually gives me a little link. If I want to click on it, it gives me a link where I can go and get more information about that function. But you can literally go through, you can literally examine every one of these hundreds of different functions that are built into SPSS. Well, one of these things, as I said, is called count. Okay, and count is equal to, okay, count gives us, count, C-O-N-T, as soon as I type in equal count, notice it recognizes after equal sign, it notices that I'm typing in something that it has functions for, count. As soon as I put in the parentheses, it then says, that's the one you want to work with. Now you have to tell me what values you want to count. Okay, and the way I'm going to tell it what values I want to count is I could type in, I want to count the number of values between A2 and A19. I could actually type this in, A2 colon A19 and close parentheses and hit enter, and actually counted that there are 18 subjects there. Now the other way I could have done that is, I'm going to highlight that again, get rid of it. The other thing I could have done there is I could have just gone up here, clicked down and dragged, and what you're not seeing there is, you'll notice that as I'm moving this, it's adjusting the cells that are affected. And then I can just hit enter. It'll give, whoops, it'll give me the same thing. Actually, hang on a second. There was nothing in those. I meant to say nothing in those cells. It actually did the right thing. There was nothing in those. There was nothing to count. There was nothing in those cells. Here we go. Okay, 18. Okay, so what is the mean? The mean is equal to the sum of all these values divided by 18. Okay, so I'm going to do those. Okay, what's the sum of all those values? Well, there is in fact a function called sum, S-U-M, parentheses. Okay, and it's asking me now to tell it all the values so it can add them together. So I'm going to get the sum of all these values. And the sum is 1799. And the average is going to be equal to the sum of all those values divided by the count of values, right? 18. Instead of putting the numbers themselves in, I could reference the cells that those numbers are located in. makes it less likely that I'm going to make an error in typing that number over. Okay, and it comes out to be 99.9 is the average for all of these values. Now, I left a little box here called mean empty because, in fact, there is a function in Excel that'll automatically do that rather than just, I did this so that we could just make sure that we understood how I got that number. Okay, and that's equals that is that we don't happen to have a function called mean. Notice nothing comes up. We do have an average, a function called average. Okay, parentheses. Okay, and it asks me to give it the numbers that I want to find the average of. So A2 through A19. And we get the same value as we did when we did it with a count. Okay, so the next thing I want to do is, that's very nice that I have an idea where the center of this distribution is, right? So, I'm going to do one more that's over here that we haven't done, median. Okay, let's find the value for the middle value here. Okay, and now there's a couple of ways I could have done this. One way is that I could have sorted these numbers, right? As a matter of fact, I'll show you that you can do that. I'm going to highlight only those numbers. I'm going to go up to data. I don't know if you can see me where I click that drop menu at the top there. It might be off of your screen. You can give me some feedback if you can see it or you can't see where I click data, and I can tell it to sort. And I don't want to expand the selection. Well, I could expand the selection because it'll sort all of the numbers that are next to it as well. Generally, you do want to sort. You do want to do that. The reason why you want to do that is because if subject two's weight is over here, you want their height over here, you want their BMI over here. You don't want to separate those numbers. So generally, you do want to expand that. In this case, I don't really need to. Okay, now they're all sorted lowest to highest, right? So the two middle values. Thank you very much, Lorraine. Thank you, Ruth. Okay, so you sort it lowest to highest. So so 18 people, right? Well, that's an even number again. So it's somewhere between the 9th and 10th person, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So it's going to be an average of the 9th and 10th person, 99 and 101. So the median presumably should be 100. Okay. In fact, SPSS Excel, has a function for median. And it'll do it for us. Parentheses, and let's see if we get the same answer. And indeed, we do get the same answer. Okay, so that's the median. That's the middle value, physical middle value of this population. In normally distributed populations, we're going to be discussing normally distributed populations in much more detail as we come up in the future weeks. But for right now, normally distributed population, one of its characteristics is that the median and the mean are usually pretty close to one another, as it is here. The mean was 99.9, the median was 100. They're pretty close to each other. When the median and the mean are different from one another, right, that distribution is skewed. Okay, and I'm going to give you an example. After we do this, I'll give you an example of a skewed distribution. Okay, so now let's take a look at this. Next thing I want to know is how variable this distribution is. If I look at this, the numbers go from 88 to 114. Okay, in fact, let's see. The minimum value, if I didn't sort it, we sorted it now, we can see the minimum value is 18. We could actually use a function, minimum, min, and we could ask SPSS to find the minimum value for us. And it does, and it's 88. And it can find the maximum value for us. And we know it's going to come up with, because we sorted this, going to come up with 114. Okay, and the range is just the difference between the maximum value of 114 minus the minimum value of 88. So one of the pieces of information that we use to determine the variability, how spread out these numbers in this sample, and presumably in the population that it's drawn from, how spread out these numbers are. One of the values that we look at is the range. What's the range of numbers that we have? The other thing that we look at is a particular part of the range called quartiles. Now, you guys know that when you took the GREs, or if you go further back when you took the SATs, you got a score, but you also got a percentile. That percentile indicated to you what percent, where your particular score was in relation to all the people that took that exam. If you were the 90th percentile, 10% of the people scored better than you, and if you were in and 90% of the people scored worse than you. If you were in the 75th percentile, 25% scored better, 75% scored worse than you. Okay, so in fact, one of the things that we're interested in is describing those quartiles. Okay, now one of the quartiles that we're interested in is called the 75th percentile, or the upper quartile. In other words, these are the people that scored or have numbers here that are in the top 75% of the values. Okay, so SPSS has about a function called percentile, equals percentile. Okay, and I'm just going to hit parentheses. You don't have to worry about that extra stuff. And it wants to know the array, in other words, a list of numbers. Well, here's a list of numbers here. And it wants a comma, and then there's a value called k. Well, k is the percentile value. In our case, it's 0.75. And I'm going to close the percentile. So the 75th percentile is 104. In other words, 75% of the people had a value above 104. So 25% of the people had a value above 104, and 75% had a value below 104. Okay, so let's take a look at the 25th percentile, the lower quartile, limit for the lower quartile, equals percentile, parentheses. Okay, and this time I'm going to go to the array. I'm going to tell it that it's this list of numbers here, comma, except this time it's going to be 0.25. Okay, so we have 104, and 25% of the people scored below 94, if this is a test or had a value below that, if it's a biological measurement. Okay, there is something called the interquartile range. The interquartile range is the middle 50% of people. Okay, this gives us the range for where the middle 50% of this sample, and presumably by inference the population, is going to be. So conveniently, I just happened to figure out what I needed to find the middle 25%. The 75th percentile, right, minus the 25th percentile. So the interquartile range is 9.5. In other words, a range of 9.5 numbers is the difference between the 25th percentile person and the 75th percentile person. Okay, and 50% of the people are within 9 or 10 of each other in this range. Okay, now what would it tell you if that interquartile range were 100 instead of 9.5? Well, it would tell you that the numbers are much more spread out. The range is much wider, and so on and so forth. Okay, so this is all a measure of variability that we're looking at right now. Where we're looking at central tendency, we look at usually at mean and median. Okay, when we're looking for the variability, we're usually looking at interquartile range, the interquartile range, and so on and so forth. What we're really interested in, though, eventually, is a special set of calculations called the variance and the standard deviation that are going to be enormously useful to us as we move on. Okay, now I know a lot of you guys have taken statistics before. Some of this stuff may seem relatively simple to you. However, I always like to start with this stuff because we could go on for an entire semester without anybody ever actually sitting down and calculating a variance or a standard deviation, just getting it from a computer program and not really understanding where it actually came from. So now we're going to calculate that variance and that standard deviation. We're going to create a measurement which gives us a good idea, a good measurement, a good handle on the variability of a distribution of numbers. This particular group of 18 numbers is the one we're going to work with. Okay. Well, first thing I want to do is I want to say to myself, well, what's a good way of describing how different these numbers really are from the mean, from the middle value? Okay. Well, a good way to do that would just take each number and subtract it from the middle value and see how big the difference is. That difference, in other words, if they're much different than the middle value, the mean, then it's more variability. If it's a small number, then it's less variability. So I'm going to fill this bar, I'm going to fill this column next to the values with X bar, with the mean. Okay, I'm going to click in here, I'm going to type in equals, I'm going to go down here and click into my 99.9, okay, and I'm going to hit enter. Okay, and then I'm going to click in here again, I'm going to drag down, and I'm going to fill that number down. Now, many of you know that when I fill that number down, okay, there's a little fill button here on my Mac. There's several ways to do fill down, left, right, and so on and so forth. On the PC, this button, this fill button is on the right hand side of your ribbon. Okay, it's all the way over here on the right hand side. Okay, on the Mac, it happens to be on the left hand side. If I can think of differences between Mac and PC, depending on what machine I'm using at any particular time, and I may change machines every once in a while just so you guys that have a different machine or an operating system are not out in cold. Okay, but it shouldn't make too much difference it'll make almost no difference with SPSS. They're identical on SPSS. Cell's a little bit different, just things it work exactly the same way, but sometimes different devices are in different places. So I'm going to say click fill down. Okay, so I would expect it didn't copy down that 99, did it? Okay, something happened there that's a problem. Okay, now we're about to learn something that may actually be useful to some people that are pretty sophisticated Excel users. What happened there is Excel has a special function in it that allows you to copy formulas with corrections down through a column. Now, I'll show you why you might want to do that. Okay, let's say that we're looking at items in a list. Okay, item. Okay, number of items, and we're looking at the cost of each individual item, and we want to know what the total cost is. Okay, let's see, 3 items at $55, three items at $110, 4 items at $66, and 7 items at $120. Okay, let's say I wanted to calculate the total cost for all of these. Well, I know I can just simply type in here an equal sign and say the total cost is 3 items times $55. Okay, total cost on that row is $165. Well, I would then have to go and compute the same formula for each one of these rows. Since people do this a lot, it could be a list here, 1,000 rows long, right? So it's very inconvenient to have to redo that formula constantly. Okay, I'm going to click down and I'm going to drag down. Okay, and I'm going to say fill down. Well, you'll notice it didn't attempt to copy that 165 down into each one of these different columns. If that 165 were all by itself over here, and I did the same thing, said fill down, it just copies the number. But since this is next to 2 numerical columns, what it does is if you look into this little window up here, what it's done is it's taken my original formula, D27 times E27, and it's taken it, instead of copying it exactly the same way, it's made it D28 times E28, and D29 times E29, and E30 times E30. So it's intelligently adjusted that formula as it's dragged down. Well, unfortunately, what's happened here is when we tried to copy this number in here, B21, when we asked it to copy it down here, right? What it's done is it's moved down one row all the way down here so that it's picking up rows that have no values in it. Okay, so I have to tell it, when I want to keep this number exact, I want the number that's in B21, that 99.94. I want that number to be present in each one of these rows. I don't want you to move down the way you would do with another kind of calculation. Okay, and the way that I do that is when it does this, kind of movement, when it adjusts the formula as you move down, that's called the relative addressing. I don't want it to do that. I want it to keep that same cell echoed in each one of these other cells. We want what's called absolute addressing. So what you do is you tell it to not to change that number by putting a dollar sign in front of the B and putting a dollar sign in front of the 21. And that tells it, oops, oops, let me go back up here. I messed that up. No, I didn't mess it up. There it is. Okay, good. Dollar sign in front of the 21 and dollar sign in front of the B. That tells it don't change that value. That's exactly the value I want. So now when I click down in here and drag down, I'm going to say fill down, and it's going to copy the same number down. It's not going to try and adjust the formula. Has anybody learned something from that that's useful to them, do you think? I'm hoping that some of you guys that use Excel, I know for me it was a kind of an eye-opener knowing that you could force that to keep it from moving the formula down. Does that help anybody out? I guess everybody is smarter than I am. You knew about that way ahead of me, right? Okay, good. Okay, so at any rate, I'm gonna also go up here and I'm gonna change the formatting in here because I'm gonna get tired of looking at all these decimal points. Okay, now I went up to format cells. You guys might have seen that. And I went to numerical and I changed it to one decimal place. Interestingly enough, if I click in here, it's all, well, you won't see it here. You'll see it down here, I think. No, that you'll just see the formula. Trust me on this. Even though I've rounded it, I've asked it to truncate it to show one decimal point, round it to a single decimal point. The information is still in there for all the other decimal points. It doesn't lose that information. Only the display has been changed to one decimal point. Okay, so now I said that one of the measures of variability that I might use is the difference between each individual value and the mean, which is going to be x minus x bar. So that's going to be equal to each individual value minus the mean, 99.9, right? Okay, let's see what I get. Okay, for that one, it's minus 11.9. I'm gonna fill that down. Okay, in this case, we do want it to use that formula. You'll notice that, over here it's 14.1, 114 minus 99.9. And these numbers represent differences between the mean and and each individual value. Okay, so now why don't I just add these together? And if it's a big number, it's going to wind up giving me if it's a lot of variability, wind up giving me a big number. Well, what's going to happen if I add all these together? Anybody want to hazard a guess? Right, exactly. The dollar sign makes sure it doesn't change. Anybody want to hazard a guess what's going to happen if I add all these together? All these differences between the individual values and the mean? It's going to add up to 0. Right, so that's not going to be a very useful measure of variability, is it? Okay, well, there's a couple of things I can do here that may adjust that for me. One thing I can do is take the positive values. In other words, ignore the negative signs, and work with the positive values. But one of the things that we do frequently in statistics to get around this problem is instead of taking the positive value, we square the value. If you take a negative number times a negative number, it becomes a positive number. If you take a positive number times a positive number, it's a positive number. So if I square each one of these, I'm going to take this value and multiply it by itself. And now I got a positive number. I'm going to copy that all the way down. Okay, edit. And I'm going to go to fill down. Okay, so I've taken the square of all these. So what do I have here? I have the differences between the means and the action and each individual value. I have the square of the differences between the means and each individual value. And I have the sum down here. I'm going to add them all together. The sum of the squares of all of the differences. That expression, sum of the squares of the differences, sum of the squares of the differences, is the first important measure of variability that you have that we use constantly in statistics. Okay, now you might say to yourself, but that number is blown all the way out of proportion because we squared all of those numbers, right? That number is just like way beyond what the differences really are. So maybe what I should do is, well, before I do that, let me think of it this way. That's the sum of all the squares of the differences. Let me find out what the average sum of squares is. In other words, we have 19 values. Let's find the average for this, right? We just add these together just like we would find an average before. I'm going to take the 829 and divide it. Well, you want to know something? For a variety of reasons, I'm not going to divide by 18, which you would expect that I would be most likely to do. Okay, I'm going to instead divide by 17. Okay, 17, you'll notice when we go back to the formula, you'll notice that that's n minus 1, the number of values minus 1. It's got something to do with this concept called degrees of freedom, which we'll explain in more detail as we go on through the semester. For the moment, you can think of it this way. If I have one number, I don't have any degrees of freedom. That value can only have one number. If I take a sample and I have two numbers, well, now I could have one or another number. I have 1 degree of freedom. If I have three numbers, well, I have 2 degrees of freedom. So you can kind of look at the number of degrees of freedom as the sample size minus 1, n minus 1. So instead of dividing the sum of the squares by n, we're going to divide it by n minus 1. Also, there's a lot of other mathematical reasons why this is going to work better for us in the long run anyway. So that value is 52.5. We're going to give that value a name. We're going to call that value the variance. Okay, so from now on, when we calculate the variance, this is what we mean. Okay, we're going to. This is the process we've gone through. We've subtracted each individual value from the mean. We've found x minus x bar. We've squared that. We've added up all the sums of the differences. We divided by n minus 1. That's our variance whenever we calculate it. Okay, so now again, I started to say before, a little prematurely, that number is kind of inflated a bit because that number is large partially because we're dealing with squares of the differences rather than the differences themselves, right? So what we're going to do now is we're going to take that value and we're going to find the square root of it. And just as aren't we lucky we're using Excel, there is a function in Excel called square root. It's kind of like a little abbreviated SQRT parentheses, and now we just want to know the value, that's 52.5. The square root of 52.5 is 7.2. Now that brings that number back down into the range of values that we're working with there. Okay, away from the squares, now back down into unsquared numbers. Okay, that's our standard deviation. And our standard deviation is probably one of the most important values that we're going to be working with going forward. Okay, so that's where we stand on that. So we've learned how to calculate the mean, the median, the sum of squares, the variance, the standard deviation, the percentiles, the interquartile range, maximum, minimum, so on and so forth. We've learned all of that, how to use Excel to do all of these calculations manually. I don't know if you read that sheet that I posted for the first session, shows the mechanical calculator. It was actually electromechanical. It was electrical. Had a motor in it. You press the buttons and hit a little button, and the ground went grinding away. But when I took statistics first time in the late 60s, that's actually the machine I was using, and we would actually do all this manually. Unless you had access to a mainframe computer, we didn't have desktop computers or laptops or anything like that then. We didn't even have electronic calculators. We would use slide rulers back in those days. Although we were right on the cusp of getting electronic calculators, we did get those by the time I graduated. But at any rate, we would have done all of these calculations completely manually. We have a big advantage on this. Even just Excel is an immense advantage. So I'm going to close this. You guys can do this. If you haven't been doing it with me, I encourage you to go ahead and do this because it's good practice in learning Excel if you're not that familiar with it, and in understanding where these numbers come from, where variance comes from, where standard deviation comes from. Let me go back to this. And just to show you this formula, the variance, well, let's see, what do we have here? Xi is each individual value. That's X, right? I is 1 through 10. In other words, we had 18, so N is 18. So from the first value to the 18th value for X, we're going to take that value minus the mean, right? We're going to take it, then we're going to square the difference between them. We're going to add up all the differences. That's our sum of squares on the top, and we're going to divide by n minus 1. That's our variance. That's exactly what we just did. If we look at this formula, if we take that formula, stick it underneath here, all we're doing is taking the square root of the variance to get our standard deviation. So we literally, what's going on in these ugly equations with all these Greek letters is literally what we just did. Okay, and again, measure variability, range, right? And so on as percentiles and the interquartile